back, everybody. Welcome back. Hope you're all feeling nice and refreshed. We've got a lot more great content for the rest of this morning, and let's kick it off with Mo Morsi. He's the founder and CEO of DevNull Productions, and Mo's going to talk to you about the history of blockchains and the XRP ledger in particular, and then he'll dive into the guts of the code that runs on the XRP ledger. With that, Mo.
Thanks for coming, everyone. It's a great honor to be here amongst the many esteemed presenters at this inaugural Apex conference. My name is Mo Morsi. I am founder and CEO of DevNull Productions, and today I'm going to be talking about how the XRPL works. This will be a technical talk. We will dive into code and various other technical aspects, but I do want to share this in a way that everyone can derive value from it. So without further ado, let's begin. Let me ask, which way ought I to go from here? Well, that depends a good deal on where you want to get to. In this talk, we're going to be talking about the history of the technology, our roadmap, which has led up to this point. We're going to be exploring Byzantine fault tolerance, what's that mean and what's entail. From there, we're going to go onto the blockchain and segue into the XRP ledger, discussing the various subsystems which constitute it. A little bit about us. We're a core contributor to the XRPL ledger with many years of experience in the industry. We're one of the organizers of the New York City XRP meetup. Our next event will be in the November timeframe, and I'd like to invite everyone to attend. We maintain XRP Intel, which is used to provide various data and metrics around ledger activity, and we're the go-to source for independent XRP developments. Contact us for a consultation today. If there was a way to go back and do it over, would you? Cryptography and ciphers have been used for millennia in a variety of contexts. The applications run from politics and warfare to economy and much more. The 20th century saw a rise in the use of transistor electronics, and the processing power increased exponentially. Now cryptography and its applications were available to the masses. The 80s and the 90s saw the rise of the consumer-grade computational market. Now computers were more integrated into our lives than ever before. Subsequently, parallelization and distributivity became important subject matters. Interconnected networks meant that we could tackle larger problems than ever before, but this required innovative solutions in order to do so. In 1982, researchers working at SRI International on a NASA-sponsored project dubbed the Byzantine generals problem. This was used to model systems engaged in distributed consensus. To quote from the white paper, there are at most M traders, and since there are more than 3 M generals, we may apply the induction hypothesis to conclude that the conditions are satisfied. Well, what does this mean? You need at least 2/3 of the decision makers in a system to be trustworthy for distributed consensus to work. Nodes in the network relay messages, nodes that are implementing Byzantine consensus, to each other. These are used to modify a state machine based upon agreed parameters. Lifecycle operations occur in discrete phases such that nodes can be assured of compliance by their peers. After this, the 2000s saw the emergence of BitTorrent and Bitcoin. These decentralized protocols facilitated the transfer of content and value around the world. Trust in the network is now paramount. The economic models of the past have been upended. This brings us to the blockchain. There are many ways to model the blockchain, but in this talk we're going to be discussing it as the intersection of state, communication, and consensus through which that state is modified. Nodes, and depending on which blockchain we're talking about, these can refer to miners in the case of proof of work, stakers, or validators in the case of XRP. They maintain a database of state information which clients modify in finite ways. Identity between those nodes is established through cryptography, which is also used to track changes in the data set in an immutable way. Finally, those changes are transmitted through the network in a peer-to-peer manner. So the XRPL implements a blockchain whose state is modified through Byzantine consensus. Transparency and decentralization means that the network operates without any single point of failure or a single authority. The RippleD codebase implements the algorithm, and we're going to explore that now. Day destroys the night, night divides the day. Try to run, try to hide. Break on through to the other side of the XRPL. RippleD implements the XRPL standards. It's written in C++, one of the most popular programming languages in the world, and is supported on Linux, Windows, and Mac OS. The cross-platform CMake build system is used to compile the source code into binary. See the CMakes list.txt file, as well as the build CMake directory for the installation logic. Here we see the definition of the core RippleD component, as well as some compiler definitions. C and C++ applications start their execution at the main entry point. This is defined under source ripple app main/main.cpp. Here we see some initialization logic, after which point the run method is called. Run parses the command line parameters, and we go from there. After initialization, control is handed off to the application class, who is responsible for maintaining the state of the application through its lifecycle. Various members of this class are instantiated, and these are responsible for governing the various systems, the subsystems which constitute the XRPL, and many of these derive from the stoppable interface. This allows the application to be stopped in a controlled manner when the administrator executes the command. And then now we're going to go into these various subsystems in the next slides. I do encourage everyone to view and to explore the code base on GitHub. It's open source technology after all. By doing so, you are empowered in order to see how the XRPL works, and the mystery kind of vanishes behind it. Also on XRP Intel, we have a source code analysis which we invite all to read. Exploring consensus a little bit more, here's the class relationship between the relationships between various classes in the application. At the bottom, you see the application itself, which has handles to the transaction queue, the ledger master, the consensus class, and much more. These images and this analysis is also available on XRP Intel. Source Ripple consensus contains the consensus logic, which actually modifies the ledger to incorporate queue transactions. On the right, we see an enumeration of the various phases of consensus as we go from the open phase to establish to accepted, and then rinse and repeat. Again, exploring consensus, we see the logic flow of the operations. Application launches begin consensus, calls out to that method, as well as launches an asynchronous timer, which is used to periodically jump into the application at various points in time. Begin consensus sets the phase to open, and then when the timer is invoked, we check the phase. If we're in the open phase and it's now time to close the ledger, we set the phase to establish, we apply held transactions. Once again, when the timer is invoked, we check the phase. When we're in the established phase, we update our positions, the positions of other nodes on the network. We set the next ledger close time, and we rinse and repeat. So to quote from one of the pivotal white papers on the topic of Byzantine fault tolerance, the replicas move through a succession of configurations called views. Views facilitate controlled access to the ledger such that data may be read and written to in a controlled manner and rolled back if necessary. So application has a handle to open ledger. Open ledger has a handle to open view, which derives from read view. Also has a handle to apply view, in which the transactions are applied. But we've only just begun to go down the rabbit hole. Data is modified through serializable data types that are persisted to the disk. The base class of this is ST-base, serializable type base, through which other subclasses implement the various data types that the application uses. Here we see representations of accounts integers, strings, and more. The node store is a subsystem responsible for persisting the binary object to the disk. Currently, it implements two backends, RocksDB and NewDB, but it being open source software, everyone is welcome to extend it to add whichever backend that they so choose. RocksDB was developed by Facebook and allows data to be read, written, and most importantly, deleted, such that nodes can discard old data to save disk space. NewDB facilitates efficient access, optimized access to large data sets, but conversely, data cannot be deleted and it takes up more disk space. Currently, full history nodes require the use of NewDB. Transactors. These are invoked during the consensus process to actually apply transactions to the ledger. Each transaction type has its own transactor. These occur in three phases: pre-flight, pre-claim, and apply. On the right, we see the logic behind the pre-flight phase of the payment transactor. And this is responsible for ensuring that that the transaction is in compliance with basic checks of the system. If a transaction fails this, then a fee will not be consumed and the transaction will not be relayed across the network. Next, pre-claim is responsible for checking the node store database, ensuring that the transaction is consistent with the state. If transactions fail this phase, a fee will be consumed, and these transactions are propagated across the network. Finally, we see do apply, where the actual meat of the transaction occurs and the transaction is applied to the blockchain. So here we see a breakdown of the three phases for the payment transactor. Note that this is not an exhaustive list. This is just cherry-picked for demonstration purposes. So in pre-flight, we ensure that source and destination accounts are valid. Source and destination amounts are greater than zero, if we're sending or receiving XRP, payment paths are not specified, and much more. In pre-claim, we ensure that if we are not sending XRP, the destination account exists. If we are sending XRP to an account which doesn't exist, we're at least sending the reserve requirements. That if the destination tag is required, we specify it, et cetera, et cetera. Finally, in the apply phase, we actually create the blockchain account if it doesn't exist. If it does exist, we update the blockchain account, we charge the fee, we credit the destination account, debit the source accounts, and more. Continuing on, the overlay protocol. The overlay protocol is responsible for communication between nodes in the system. It transpires via a protobuf encoded message stream through which a SSL connection is established, a handshake occurs, and then communication happens. On the right, you see an example from our Ruby library, the XRBP interface to the XRBP library, which is the Ruby interface to the ledger. At the top, you see the SSL connection being established, and at the bottom, you see the actual handshake, what constitutes that. From there, the protobuf messages are sent and received, and those consist of a 32-bit message length, a 16-bit message type, and you see the enumeration of those on the right, and then the actual message contents. And here's an example from our Ruby library where the connection is being established, the handshake is occurring, and we're dumping out messages to the console. Finally, we'll wrap up with some additional topics. Obviously, we're limited time here, so we can't explore everything. But the RPC interfaces, any language that has a WebSocket library can communicate with the XRP ledger. RippleLib, which actually has been renamed to XRPL.js, is the JavaScript and the TypeScript interface. XRPL.py is the Python interface. XRBP, as I just mentioned, the Ruby interface. Many different cryptography, two different cryptography formats are supported. SEP256K1, which is the same format that Bitcoin supports, as well as ED25519, which is more resilient to attacks from quantum computers. Path selection, there's a lot more that goes into it. I encourage everyone to explore the code on your own. And with that, it's closing time. You don't have to go home, but you can stay here. Thank you all for having me. Happy to take any questions, either right now or via email, and that's it.